So my name is Kirill, and today I'll tell you about sparse variational dropout and variance networks. Dmitry just already told you about Bayesian neural networks, about high-level concept of Bayesian neural networks, and I'll tell you explicit examples of these Bayesian neural networks, and we will see some intuitive and counterintuitive results, and then you'll have a seminar where you can code it by yourself. So we will talk about, firstly we will talk about variational dropout. That's the ancestor of all the Bayesian networks, I think. And then we move to the improved version of variational dropout. That is sparse variational dropout. And as we are going to talk about sparsity, I decided to make a brief overview of other compression methods, of course Bayesian compression methods, because we have Bayesian deep learning school. And finally, we will see a very intuitive model with very counterintuitive results. So let's start. Let's start with variational dropout, and to motivate variational dropout, we need to have a look at Gaussian dropout. And okay. Because I have an animations on the slides, but it broke because of converting to PDF, I think. So let's pretend we don't see this. We see on the upper part of the slide. And what we have a Gaussian dropout model where we have an input of our layer. We multiply it by our weights, add some multiplicative noise, Gaussian noise, and obtain activations and then apply nonlinearity. And what's the motivation of Gaussian dropout? That's the same as binary dropout. We just want to regularize our network. But let's take a look at this thing at slightly different angle. Let's say that instead of multiplying by weights and then applying noise, we just sample weights from this distribution. It doesn't change the mean value of our weights. It adds multiplicative noise, as Gaussian dropout does. And then it samples from this distribution, where we have W hat mean and such variance. And what we just did, we just defined our approximate posterior distribution. What you are talking about at the previous lecture. And for now, we are in one step from defining our first Bayesian neural networks. Let's define it. Slide looks very complicated, but let's take it part by part. So we have an elbow. Here we have approximate posterior of our weights. So that's W, that's parameters of our network, neural network, of course. And phi is the parameters of our posterior that we want to find. And that is the output of our network. Let's say that's probabilities of classes on MNIST dataset or CIFAR-10. And then we also have, just like in ELBA, just like you know, we have chiral divergence between approximate posterior and prior distribution. And we want to maximize it with respect to phi, where phi is the parameters of our approximate posterior. So we define posterior distribution like in Gaussian dropout style. We obtain our sample by multiplying mean values by some noise. That's actually Gaussian dropout noise, but with only one difference, that we have now individual alphas for all the weights. We have alpha ij for the weight or parameter wij. And now we have approximate posterior distribution for our weights. That is. So what we need else? We need to define our prior. our prior to our weights. And let's say it will be log uniform, just like this and just like on this plot. And you can ask me why we take log uniform distribution, and I'll answer that we want our KL divergence doesn't depend on our weights, on Wij, on means of our weights. So that was original motivation of Kingma, Salimans, and Welling. Then they made this paper, Variational Dropout and the Local Reparameterization Trick. They want this KL divergence to be constant with respect to Wij. So if we fix alphas, if we fix all alphas, we just optimize neural network like we did in Gaussian dropout, okay? Because this is constant with respect to Wij. I hope it's clear. Let's look how the local reparameterization, here is local, local reparameterization combines with variational dropout. Once again, we have distribution on our weights, for example, normal distribution, and like in variational dropout. And we want to calculate BI, that's the activation that is scalar product of the column of matrix W and input vector X. We can split this sum into sums, and we can see that here we have just standard normal distribution. And from basic course of probability theory, we know that we need to sum up all the variances to obtain the variance of resulting distribution. And we just can add the mean. So we have this distribution on BI. And instead of sampling each epsilon ij, we just can sample one single BI from this distribution. And what variational dropout says, it says that we need to sample each weight Wij from this distribution. Then we need to multiply matrix W by matrix X and obtain output, and then apply nonlinearity. And what local reparameterization trick says, it says that we can pre-compute our mean of our output, pre-compute our variance in this manner, and then we can apply nonlinearity, and we will obtain the same result. So far, so well, but we have some problems. Because, for example, we have problem with variance reduction. We want to calculate partial derivative of our loss function, of our alpha, yeah, to perform gradient step descent, We want to obtain this partial derivative, and it depends on this partial derivative of single sample, Wij, that's a single sample from our distribution, that is calculated in this way. And we want to we want to take partial derivative of this formula with respect to Wij hat. That's the mean of our distribution. Okay? We take this derivative and we see that this term is very noisy. The larger alpha we have, the larger noise we have. So at some level, at some values of alphas, we just have a random walk. And that's not what we are looking for. Not what we are looking for. It prohibits to use large alphas. So Kingma said that, okay, let's clip alphas from 0 to 1, and we will be fine. But we are not fine because it prohibits to use large alphas, and one can ask, why do we even need large alphas? And let's take a closer look. We optimize elbow once again. We optimize it with respect to our means and alphas. And here we have negative KL term, and this negative KL term behaves like this. it pushes alpha to big values. It pushes alpha to infinity. And on this plot, we have really big values because it's logarithmic scale on alpha. So here, for example, we have something like 10 power 8. That's almost infinity for us. And what happens if we have very large alphas? It appears that very large alphas severely corrupts our data term. Because here we have very large noise with very large variance. If we have 10 power 8 alpha, it's just huge value compared to the usual values of our weights. Usual values of our weights, it's just like, it's less than 1, okay? And to prevent this thing from corrupting our data term, we just must to set this value to the 0, okay? So in some sense, we can obtain sparsity in this way. If we can have large alphas, we can obtain sparsity because of this thing, because this will happen. So the same thing can be formulated in terms of Bernoulli noise, and we can equivalently show that Bernoulli noise will give us just the probability of 0 in Bernoulli random variable will be just 1 if alpha goes to infinity. Okay, but how we can train large alphas? Because if we train like this, it's supposed that you don't see this thing, but okay. If we train alphas like this, we just can't set our means to the zeros. We can set W, here we need to set W hat ij to the 0, okay? And here the reason why we cannot do this. Because we have very noisy gradients. We have just random walk in the space of parameters. So we can hit any target. We can't hit any target in this space. And the solution is to use another parameterization of our network. Instead of using this parameterization, instead of using mean and value alpha, some strange value actually for normal distribution, let's take some more natural parameters. Mean also and standard deviation sigma ij. And if we take partial derivative with respect to W hat ij, we'll see that there is no any noise here. So we can set it to any value if we have appropriate learning rate. So now we need to optimize our elbow with respect to W hat and sigmas. Okay, and sigma is a new independent variable. And so we are talking about sparsity, and let's look what will happen. So nothing happens because gifs are not playing in this thing. Is it possible to use a PowerPoint presentation on this laptop? Yes, it is. Okay. Let's take a 5-minute break. Sorry for this break, for technical reasons. Once again, we need somehow reduce variance of our gradients, and you already know that we are going to use another parameterization, and once again, let's see what will happen. So the red pixels are positive values, blue pixels are negative values, and white pixels are 0 values. And on the left, you can see kernels of linear 5 convolutional layer, And on the right, you can see matrix of fully connected layer of lineate. And that's a training process on MNIST dataset. So we have the same accuracy. Here you can see that it's almost perfect. And on the last epoch, we almost have no weights. And we have about 270 compression ratio. So let's look at other results. Here on MNIST data set, we have two different architectures, Lineate 300-100 and Lineate 5. And we have almost the same performance of the old model. That's here is sparse variational dropout, and that's other models. And we can evaluate with approximately the same performance. We can evaluate compression ratio. That's the total number of the weights divided by non-zero weights after pruning. And you can see that for Lineate 300-100, we have the best value, 68, and here we have 280. More results on CFAR10. We have VGG-like architecture by Zagoruika, from his blog. That's 13 convolutional layers and 2 fully connected layers, and we use pre-activation, batch normalization, and binary dropout after each layer. And then we can do the following. We can take width of each layer and multiply it by some scale factor k. So we have now different architectures with different width. That's the original one, because here we multiplied all the width by 1. And here some small nets, and here there is big net. And what we can see that as this scale factor k grows, error goes down, error of classification CFAR10 on a test set, of course. Error goes down, and compression rate goes up. So our model tries to preserve the size of the network. We add some excessive weights, some spare weights, and model just prune it. And here we have blue line and green line that's just not pruned, just trained VGG-like on CFAR10, vanilla. And here blue line is sparse VD, so almost no accuracy degradation. K is a scale factor. For each layer of the VGG-like network, for each layer of this network, we can multiply width of this layer. For convolutional layers, it's number of convolutions. For fully connected layers, that's the number of neurons we have. We can multiply each width of each layer by some scale factor k. Yes, we have not sparse. We have now we are talking only about architecture. We have, for example, if you have 100 filters on all convolutional layers and 100 neurons on all fully connected layers, you multiply it by scale factor 1.5, and you obtain 150 filters for every convolutional layer and 150 neurons for every fully connected layer. So you obtain new architecture. Compression rate means if we take this architecture and train it with sparse variational dropout, we obtain more compression because we because we added some spare weights in our model, okay? Compression of zero weights. That's
no. What is compression rate? It's
compression rate. That's the same number as here. That's the ratio of total number of total weights in our model and divided by number of non-zero weights. Non-zero after training of sparse variational dropout.
And what's about sigma values after optimization?
Sigma values?
You optimize W and sigma.
Yeah.
Variances. And what's about their values?
Okay, there is some values. We have some values of sigma, but that's not big, that's not small. It's just values of sigma. It's comparable to the values of weights in vanilla network. So it's about 1 divided by 100. How we achieve specification? We achieve specification by, we already achieved specification on this slide. If we have large alphas, actually alpha, I have it on other slide, I'll tell you. Okay, I'll tell you about the meaning of alpha. 1 second. Yeah, here we have alpha multiplied by our mean squared, yes? That's equals to our sigma squared. And then we can see that alpha, 1 divided by alpha equals to our mean squared divided by our variance. That's, in some sense, in signal processing, it's called signal-to-noise ratio. So if we have very large alphas, we have almost zero signal-to-noise ratio. So we have no any signal from these neurons. And if we have some values of alpha, not zero, we have that means that's a meaningful weight. So we just after training we have 2 clusters of alphas. We have weights with very large values of alphas. That means that it's almost zero, okay? And we have weights with some meaningful values of alphas. That's just what these dots, red and blue dots. Okay, let's move on. One more fascinating experiment is presented in this paper, Understanding Deep Learning Requires Rethinking Generalization. What these guys did, they just took the pictures, took CIFAR 10, and shuffle all the labels. So there is no any dependency between picture and label. And then they train all the modern architectures until 100% accuracy on the train set. And of course, any model will have 10% accuracy on test set. And then they said that even if we have binary dropout applied to our network, yes, that's the tool for regularization, tool that's supposed to prevent overfitting of our model. But here we have severe overfitting, yeah? If even we have binary dropout here, we still can achieve perfect performance on a train set while have random guess on a test set. But if we apply sparse variational dropout, we will have 10% random guess accuracy on the train set and 10% accuracy on the test set. And 100% sparsity because sparse variational dropout just removes all the weights from the model. And that means that we just have more sophisticated or more powerful tool for regularization. Maybe not on the all data sets and for all architectures, but on CIFAR 10 and NIST, we have this tool. It works. It works better than binary dropout. Okay, do we need one more 5-minute break? Okay, we don't need it. So, as we are talking about compression methods, let's take a brief overview of other compression methods. There is method for Bayesian specification of recurrent neural networks. As you know, recurrent neural network obtain next hidden state at time step t by this formula. It takes input at the time step t, multiplies by some weight matrix, then add hidden state multiplied by some matrix from the previous step, and also we have some bias, but that doesn't matter. And we can apply the same technology here. We can apply the same concept here. We can say that assume all our weights came from this distribution, and we will train we want to find parameters of this distribution. But now we want to define parameters separately for Wx and separately for Wh. It has different meanings, and as in convolutional neural networks, we have separate distribution for layers. Here we have separate distribution for the weight matrices. And but here is a small problem that to apply RNN for your sequence, you must apply the same function to the all time steps. So we cannot perform LRT. We cannot perform local reparameterization trick because you can think of it as follows. You can think that we sample one neural network, we sample one RNN, and then apply this RNN to the sequence. So matrices WH and WX should be the same on the all time steps. Okay? So we need to apply the same matrix to every element of the sequence. And here again, we can apply the same matrix. We must apply the same matrix to the all hidden states. Okay, we cannot perform LRT, but without LRT, it gives us great results on sentiment analysis. That's the regression problem when we need to estimate some text. Is it good or bad? In sense that, for example, some review of restaurant on TripAdvisor, we can estimate the number of stars in this review. And here we have some other models, and here we have sparse variational dropout, and we can see that it achieves just tremendous values. It's almost all the weights are specified. That's sparsity. Here we have sparsity in terms of percent of specified weights. That's not a compression ratio. That's a little bit different thing, but the values are just amazing. And we have comparable performance on this task. And sparse VD, no dropout, you mean? In brackets we have the way we pre-trained our model. So here we have no pre-training. Here we pre-train without dropout, without any dropout. And here we pre-trained sparse variational dropout we pre-trained our network with variational binary dropout. That's the paper, that's the method from Gal and Zubin. And that's actually a paper from Katya Lobacheva and Nadia Chirkova, girls from our group. And one more task we have, that's language modeling. And here we have log likelihood on a test set. And we also achieve great results with sparsity. Here we have one more matrix, WY, because now we have a classification task, and we can specify one more matrix. Okay. One more interesting topic is group sparsity, because sparse variational dropout provides us with general sparsity with no structure. It just says this, you need to use this weight, you don't need to use this weight. No, any structure. No structure at all. So, and it can be efficiently generalized for group sparsity. But structured sparsity, that's a very powerful thing, that's very useful, because in these terms we can accelerate deep neural networks. We can remove some filters, or we can remove some neurons and just apply matrix multiplication on the subset of matrices, and thus we can accelerate, speed up our networks. And also it allows us to more efficient compression, because we don't need to save sparse matrices, we can just save part of our matrices, and it can be done in more efficient way. And idea of having group sparsity is very simple. We just move noise from our weights to our activations. And then we can apply the same logic here. We can apply the same logic that says that we apply noise to activations, and noise tells us which activations we need to use and which activations we don't need to use. And removing one activation, we remove the column of weight matrix W. So we remove one neuron, we remove the column, and the same applies to the filters. If we remove activations of one filter, we can just remove the filter because we don't need this filter. Because noise set our activations to 0, and we just don't want to calculate the values of this filter, because noise multiplied by 0. So, and if in variational dropout we have log uniform prior distribution and normal distribution as our approximate posterior, for log normal dropout, for dropout on activations, we have truncated log uniform distribution. That's just truncation on the support from A to B. And we have log normal distribution. It's also truncated from A to B. And we can do the same thing. We can calculate KL divergence and so on, and we can optimize ELBA. And let's take a brief look at the results on MNIST. Here, again, two architectures. We have structured BP, that's our method. And we can achieve pretty good acceleration in terms of flops here on LINET 500, 300. But we have very small acceleration on GPU because this network is very small. And here on LINET 5, we obtain very good acceleration in terms of flops, and even good acceleration on GPU. Okay, of course we have results on CFAR 10 and VGG, but that's not so interesting. I think let's move to the more interesting thing. It's variance networks. Structured sparsity learning, that's SSL stands for structured sparse learning, that's a pruning method when we train network and then just remove weights by its absolute values. And then we train it again and again, and it's something heuristic method. Okay.
And how to combine group sparsity with batch normalization methods? Should we apply it before or after it?
I think that we applied before, and that was okay. But I don't remember special details, technical details of this. But it combines well. The paper calls log multiplicative log normal no noise for structured Bayesian pruning with log normal multiplicative noise. That's the paper. So now let's move on to variance network. I promised you that I tell you intuitive model with very counterintuitive results. Once again, let's take a look at Gaussian dropout. And as you remember, we have single alpha per layer. Single alpha per layer for all of the weights. For all the weights, we have single alpha. And let's try to do it. It seems that there is almost no difference between variational dropout and the Gaussian dropout if we take single alpha per layer. And we have the same. We have the same approximate posterior. We have the same prior and almost the same Kirill divergence. But now we have only one alpha per layer. And nothing outstanding. Nothing outstanding happens in theory. But on practice, what will happen on practice? Here we have a CIFAR 10 data set, and we evaluate test accuracy on a CIFAR 10 data set. Blue line stands for deterministic procedure. That means weight scaling rule, when instead of weights, we use expectation values of approximate posterior distribution. Okay? Is it clear? I think that Dmitry Molchanov told you about it on the last lectures. And not told, yeah? Okay. Well, and we have stochastic procedure when we sample, when we take one sample from approximate posterior and we use it as our neural network and evaluate test accuracy on the CIFAR 10 using this sample of the network. Okay, and red line stands for ensembling when we have several samples from our approximate posterior, and then we average predictions of our network, and thus we obtain labels for test images. And what will happen here on the right side of the plot? Some actually weird thing starts to happen because deterministic procedure have a very steep drop. In several epochs, it goes from almost state-of-the-art performance to random guess performance. And we see that alpha constantly grows. As we learn our network, it constantly grows. And it has almost infinite values compared to the usual size of our weights. Usual values of our weights, usual magnitude. And the more interesting is that stochastic and ensembling procedure are just works fine, like never happens. It just like nothing happens, and the only thing is here is the drop of deterministic procedure. And that is really strange. Let's take a look what happened when alpha goes to infinity. Once again, as we already told, variances of our approximated posterior equals to alpha multiplied by the mean. So 1 divided by alpha, that's actually signal-to-noise ratio, because it's squared means divided by variance. And it equals to 10 powered minus 5. So it's almost 0. So we have no any signal in terms of signal processing, but our network still almost perfectly classifies all the pictures. And actually, this distribution that we have, it converges to this distribution with just 0 mean and some variance. And that's what we called variance network, because it doesn't have, we have no means anymore. We have only variances, and we train variances, and it works. Also, we proved some theorem that in terms of MMD, if alpha goes to infinity, in terms of maximum mean discrepancy, this distribution are not distinguishable. And let's take a look at the Bayesian formulation of variance network. Once again, we have elbow, which we want to maximize. Now our weights are sampled by this formula. We have variances and standard normal noise. So our weights have such approximate distribution, have this, looks like this. And let's look what happens to the prior. If we have log uniform prior, then we have constant KL divergence. So KL divergence doesn't depend anymore on our approximated posterior. Very strong sparsity inducing prior log uniform. It even cannot be normalized. It's so strong. It doesn't influence us anymore. So we can just read over it and train our data term. And then we can say that, okay, let's just train neural network like this. Let's set the distribution of the weights to be like 0 sigma squared, and let's train network like this, and we will obtain good results on classification. On MNIST, CFAR 10, CFAR 100, you can see that for any data set, for every data set, we have dropout and variance. Variance stands for variance network, because this is network that has some variance layers, and dropout, that's just a usual network. And we see that we obtain comparable performance on ensembling. Maybe, of course, not in the deterministic case, but because we just cannot use deterministic case. Because every mean of our weight is just 0. If we use deterministic procedure, we just zero out all the weight, and of course it results in random guess accuracy. But in terms of ensembling, we have very good performance. So it's quite surprising that this thing can be trained up to this performance. And then I skipped this slide because I want to tell you about results and classification. And now let's take a look at different parameterizations. It turns out that from the Bayesian point of view, we have best model here. If we set 1 alpha per layer, we have best model in terms of alpha. Also, we can set 1 alpha per neuron, 1 alpha per weight, and use additive parameterization, but this works in terms of alpha, it is best model. It is the best model. And neuron-wise parameterization pretty close to it. And you can see that the same thing with deterministic procedure happens to the neuron wise model. So it's really, really surprisingly that we can, the best models from the Bayesian point of view just cannot be applied in deterministic manner. It's okay? Do you have a question?
Yeah, just a very quick follow-up. I mean, doesn't it seem very counterintuitive in terms of that the likelihood with more parameters can have, I guess, but does it mean that we are simply stuck in some local extrema?
Yeah.
And the problem is not parameterization, but the algorithm for the search, right?
Mm-hmm. Yeah, sure.
Yeah, I saw that afterwards, so that.
Yeah,
I mean,
that's the exact thing that happens. We just stuck in the poor local minimum because we have too much parameters. And we over-parameterized our model and stuck in the poor local optimum. So that's really counterintuitive. Here we have less parameters, but have better value of our function. So let's move on to the intuition of the variance networks. Let's consider some toy problem. Here we have just 4 Gaussians, 4 classes. And let's take some model that takes X as input, do something. So we have some layers here. Then we have a bottleneck layer here that has only 2 activations. And then we have a classification layer here to classify it in 4 classes. Let this layer be variance layer with output A1 and A2. And after training this network, we can see we can build the same plot for every object. We can build a scatter plot in terms of A1, A2, okay? And that's how it looks. We have 4 distributions with 0 mean. Each distribution has 0 mean on both axes and different variances. And that's what our network does. It tries to classify distribution by its variances, not by its means, but by its variances. And that's pretty cool. One more thing I want to talk about, that's information flow from means to the variances. Here we have 4 lines. Deterministic, blue line stands for deterministic procedure. You already know what it is. And you also know what is ensembling. That's the orange line, but you don't see it because it always works perfectly. It's just behind the other lines. It's here. And we have D0 line, that's the green line, where we do the following. We take our approximated posterior and set all the expectations to the zeros. And then we sample from it. And sample and evaluate accuracy on a test set on a MNIST data set. Okay. And also we have a red line that stands for permuted sigmas. So again, in a single layer of our network, we can take approximated posterior distributions and just shuffle all the variances. Then take a sample, then evaluate test accuracy. And what we see that here, in the beginning of this plot, we have all the information in our means. And that's already pretty intuitive, because deterministic procedure works well, and sampling procedure works well, it always works well, And D0 procedure doesn't work because we zeroed out all the expectations, so we just removed all the information about data set because information was in these expectations. And permuted variances also works well. And at the end of the training procedure, we see the opposite picture. We see the picture when deterministic procedures and permuted sigmas results in random guess accuracy. But D0, when we just removed all the expectations, works perfectly. And one more thing, we have here interesting phenomena where we have such epoch at which both deterministic procedure works well and D0 procedure works well. So information is concentrated simultaneously both in expectations and in variances of our model. And that is really, really curious what happens here, what's the network is that. So to conclude, I want to summarize. Here's a smile, but it doesn't matter. To conclude, I want to summarize. We just discussed variational dropout as one of the first examples of Bayesian neural networks. We see that a lot of different models with totally different properties appeared from variational dropout. We see sparse variational dropout, but Bayesian specification of recurrent neural networks. We see group sparsity, Bayesian group sparsity, and we see variance network, very counterintuitive model that results in state-of-the-art performance on many tasks and that has best elbow possible in terms of variational dropout. We also see that variational inference is a powerful framework for building Bayesian neural networks, and it looks pretty simple, but it requires it requires very hard attention to the details, such as variance of the gradients and inference on the test stage. Also, we saw that we can efficiently store information in the variances if we remove all the means. Of course, we store information in the variances. And one more thing I want to talk about, that don't forget about pitfalls of weight scaling rule. So on this plot, if you have a deterministic procedure on a test stage where you just take expectations of your approximated distribution, of your approximated posterior, you can see this picture. You can see the steep drop of deterministic procedure. But that doesn't mean that your network doesn't work. Maybe in ensembling, it works perfectly. And that's all for now.
Hello, thank you for your talk. Very interesting. I have a question. So you say you have these properties and you show them on MNIST. Have you investigated them on more complex data sets such as CIFAR10, ImageNet, or for other tasks like
these
language
properties,
modeling?
you mean?
So you just had.
You mean these properties? That's the on CIFAR10.
So there's like at the end you had these graphs near the end.
Okay. This.
Yes. These. Yeah. For
this,
example.
Yeah, that's a good question, because on MNIST we have such network, and on CIFAR10 the picture looks different. We have no such network that works both in variance mode and in the deterministic mode.
Okay. I mean, I think more generally what I'm getting at is, have you applied these models to much more complex tasks and data sets?
We didn't apply it, of course, for ImageNet, but we applied for CIFAR10, CIFAR100, and it works. It works in ensembling. It just works. For CIFAR100, it even works better than dropout. And also we applied these techniques for reinforcement learning, for adversarial attacks, and for different settings, but and it works comparable with state-of-the-art results, but I just decided not to include it in the presentation.
Thank you.
You can see it in our paper, Variance Networks, when expectation doesn't meet your expectations. Yeah.
Yeah. Thank you for a really nice talk. Can we go back to slide 25?
25, okay.
Yeah, with all of these graphs, right? No, no, a bit later. Perhaps it's next. Right. Here, where the accuracy drops on the empirical mean estimates, where you plug in empirical mean. Well, I guess I made this comment already, but I guess it's important to pinpoint that I believe that it's just a property of that mean is a non-informative statistics for a very flat distribution, right?
Yeah.
And I guess that the thing that I would just suggest right now would fix this drop in the accuracy. So if you just only plugged in the empirical mean estimates for those layers or those weights that don't have a flat posterior.
Yeah, yeah. That's a very good remark, because
yeah, then this would fix the issue. And only plug the empirical mean for the informative posteriors or for the concerned posteriors, which are not flat. Then I guess this issue wouldn't have happened.
Yeah, yeah.
And then
one more thing on this remark, that here we have large dimensional space. And if we sample a point in a large dimensional space from normal distribution, we have zero probability to hit the mean. Because it looks like bubble in a large dimensional space, I think. That's all.
Hello. So my question is in regards to the experiment comparing, rethinking the generalization
Okay.
and sparse variational dropout. So there in their experiments, they showed that regular dropout and adversarial noise training helps to reduce the memorization.
Adversarial noise training and...
Yes,
okay.
and dropout. And similarly, in sparse variational dropout, you seem to obtain sparse filters, right?
Yeah.
And you see you get the same observation when you do adversarial noise training. So I was wondering if there is any work to try to reverse engineer some sort of prior that would be similar to adversarial noise training, which might be more formal way of compressing neural net.
More formal way of adversarial training, you mean? Yeah.
Yes, yes. From Bayesian perspective, let's say, because it seems like there is some sort of similarity in terms of prior that you induce on your neural network.
I think that will be interesting. I haven't heard about such priors that. But that's how people actually sometimes do. They reverse engineer some known methods and understand what prior is it.
Because it seems like there is some sort of might be some sort of
maybe.
Okay, cool. Thanks.
And if we compare with conventional neural networks, just this architecture, it requires sampling. And in conventional neural networks, we can make a prediction in one pass. So it's more efficient.
Yeah, of course.
What benefits can you say that make it reasonable to use your particular architecture if final accuracy is the same, state of the art?
Are you talking about sparse variational dropout or about variance networks?
Well, in general, approach in variance, for example, when we teach by variances.
In general, my answer can be different, because in case of sparse variational dropout, I can say that we can use sparse variational dropout because it allows us to get sparsity of our model that the conventional method doesn't. In case of variance networks, of course, that's the application of it is very questionable. But I think that most interesting result is, of course, here, because we just We just show model that where weight scaling rule cannot be applied. That's the one point. The second point is here, where we show that from the Bayesian perspective, we have best model in terms of alpha. It achieves best value of alpha. So I don't think that in current state, variance network are a very practical thing, because of course we have comparable result, but only for ensembling. One thing you can do here, it's to distill, to train a network, deterministic network, that will resembles this ensembling. But the purpose of it is not clear for now. And I think that variance network not more about applications or on practice. It's more about our intuition in Bayesian neural networks. It's more about it's more about science. That's just a funny experiment.
And the second question is about sparsification. Did you compare your scheme with the L1 regularization of conventional
with
networks? What? L1 regularized conventional networks.
Yeah, of course. That's not. For example, here, and also we compared, I think on CIFAR 10 with other methods. Here you have pruning, and that's software sharing. That's for compression, method for compression. It not exactly removes some neurons, but it maps weights in other space, in more compression, it somehow compress weights for now. And DNS stands for deep neural specification. So we compared with conventional methods that allows prune networks. So we compared with pruning, and also here that's structured sparsity learning. That's also pruning method. Where is? Do you have a microphone?
Another very small question. Okay. Regarding specification, does it mean that we are actually capable of getting some interpretable models at the end of the day?
If we have
very huge specification, yeah.
Yes. If we have very huge specification, I think so. But
has someone looked into that in detail and tried to
No, I don't think so.
Okay.
But that's our dream. I think that's our goal. Of course, we want to interpret neural networks, but I think maybe it's possible for small networks, just like LINET 5 here, with its tremendous compression rate, and LINET 300, 100. But I think that's not possible for CIFAR 10 for VGG-like form.
Thank you.
Large architectures, yeah.
Hi, I have a question on slide 33.
Can you take mic to the...
Can you just go to slide 33?
33? 33? Okay.
Yep. It's about the toy example. And you gave an intuition in the next slide about the spread of the variance, right? So I just wanted to know how dependent this is on the depth of the network you have used. Like, if you go back to 33 again.
Sorry, I haven't got your question.
If you go back to 33.
Okay.
So how dependent is the image you show in the next slide, dependent on the size or the depth of the network?
How this image depend on this network, yeah?
Yeah, on the depth of the network.
So,
Let us say DI is...
we have a network, and we have a bottleneck in this network. So we have a layer with only two activations, A1 and A2. Then we can take any point from our data set. That's our data set, okay?
Okay.
We can put in our network. It goes through all of the layers, and then we can take a look at the A1, A2 for particular point. And then we can plot this point in space A1, A2 on a plane. Okay?
Yeah, now if I choose a different network, but the same bottleneck, if I use a shallower
Different data
here,
set, you mean?
No, different architecture for
Different
the network here.
architecture, yeah.
Yeah, let us say I just use 2 layers instead of 5 layers. Do you think it will still be the same?
I think so. Actually, we just made single experiment with this thing. We had 6 layers, and 5th layer was a bottleneck, and we see it and just said it's okay. We don't explore this hardly, but I think yes.
Hi, thank you for your talk. So my question is whether it is possible to extend this approach for generative models. I mean, for example, can we using like this approach for optimizing the size of the bottleneck, for example, in the autoencoder or something like that?
Size? Oh, yeah. Yeah, I think maybe we can. We didn't try. But I think we can.
Wow, okay.
In some way.
So actually there is a paper that does exactly what you asked for. So it applies a model similar to the relevance vector machine to a variational autoencoder, and it uses it to automatically determine the size of the hidden space. So it is possible, yes.
Hi, I have a question regarding sparse networks. And have you tried trying to recover which patterns they learn via, for example, saliency map or guided backprop? Because I can hardly believe that convolutions with just one non-zero weight can detect something interpretable. Or that's a question. I don't mean different filters, but what network, which patterns network learns in general.
We didn't explore that. So here we doesn't care about which patterns network learns, because usually people care about performance. And
okay.
We also cared about compressions and acceleration. So that's not about interoperability of the network, I think. Actually, here I think it could be a group of neurons that's maybe not a single weight. That's maybe a group of weights. Okay, I think that's all for the questions. So have a good time.